Here, in electromagnetics, optics fails to explain absorption, emission, and photoelectric effect of the light. The quantum optics deals with the light as a discrete quantity, as quantized and light energy. Major contributors of quantum optics are Albert Einstein and Max Planck. Quantum's perspective, light consists of particles called photons. A photon carries electromagnetic energy and momentum, as well as intrinsic angular momentum associated with its polarization properties. Here, photonic optics provide that the energy of the electromagnetic mode is quantized to a discrete level separated by the energy of the photon. The energy of the photon is given as this, which depends upon the photon frequency. Here, as known in atomic theory, what happens is when an atom may emit or absorb a photon by undergoing downward or upward transitions between energy levels. Let's say if an atom has gained an energy, it goes to higher energy levels. When an atom lost energy, it goes to lower energy levels. Three forms of interaction is possible for a photon, not an atom, so for a photon. And a photon goes to, attains energy, it goes to higher energy levels, and when a photon loses its energy, it goes to lower energy levels. Three forms of interaction are possible: absorption, spontaneous emission, and stimulated emission. Here we can see that if an electron in an atom is initially in the lower energy level and radiation mode photon contains a photon, the electron absorbs the energy of the photon and goes to upper energy level. This process is called absorption. It occurs only when the mode contains a photon, and that is in radiation mode, in the sense that the energy of the photon is greater than or equal to the separation between the two energy levels, here energy level 1 and 2. This absorption phenomenon is the working principle behind absorption spectroscopy, where incidental radiations of photon and photons are incidented on a sample, and radiation is transmitted back when the energy of the photon is much less than the separation between the energy levels, that is energy band gap of the material or the sample. In absorption spectroscopy is the method that uses wavelength-dependent absorption characteristics of materials to identify and quantify specific substances. Bayes' law is something which is Bayes' law tells us the amount of light absorbed by a sample to the concentration of the absorbing species. This Bayes' law is the main principle behind absorption spectroscopy. Here we can see that in an absorption spectroscopy is based on measurement of transmittance T and absorbance A. Here these transmittance and absorbance depends upon the solution and solvent properties. This was the Bayes' law for absorption. Now, single beam instrument. What is the single beam instrument? Single beam instrument is nothing but where we wanted to see the absorption properties of the sample cell. Here, it consists of a tungsten or a deuterium lamp as a light source, a filter or a monochromator for a wavelength selection, matched cells that can be placed alternately in the radiation beam, an amplifier, and a readout device. Here they have interchangeably tungsten and deuterium lamp sources. They use rectangular silica cells equipped with high resolution gratings for monochromator with variable slits. Here what happens is the source sends a light through the filter, and the shutter moves up and down. The shuttering mechanism is what it makes the light, the wavelengths to go here the wavelengths to go to the reference cell or the sample cell. From the reference cell we can see what wavelengths are getting transmitted and what wavelengths getting absorbed. Similarly, from the sample cell, we can see what wavelengths are getting transmitted and what wavelengths are getting absorbed at the photodetector. From this, we can say that let's say an element is absorbing, is transmitting wavelengths at 480. The chlorophyll B2B is transmitting wavelengths at 480. Then we can say that, okay, this is a chlorophyll B element. Depending upon the wavelength the sample is absorbing or transmitting, we can identify the kind of element that is, identify the kind of material it is. This is the principle of single beam instrument, and single beam instrument is a kind of absorption spectroscopy instrument. Here the shuttering mechanism is replaced by a rotating motor or a V-shaped beam splitter, which are the designs in modern instruments. And here double beam instrument, we can see that we have a V-shaped beam splitter. Here the two beams are formed in space by a V-shaped mirror called beam splitter. One beam passes through the reference solution of the photodetector and the other simultaneously transfers to the sample to the matcher detector. Double beam principle is used in UV visible absorption spectroscopy. Fluorescence is a phenomenon that a material emits light at one wavelength when you illuminate it with another. Here, let's say an electron from the ground state is excited with an energy of E1, but we can see the excited electron undergoing some it's going to one excited state to another, and from that it is emitting a photon with a different energy. This causes difference in the wavelengths, in absorption wavelength and emission wavelength. This is due to the vibration relaxation of the electron. This process is called fluorescence. A fluorescent material is called fluorophore, and sometimes fluorescent dyes, labeling reagents. A fluorophore absorbs light at lower wavelengths, and that is excitation, which is used for excitation, and emits light at longer wavelengths, that is emission. As we can see in the excitation and emission wavelengths are different. Energy is lost due to vibration relaxation or intersymbol crossing or interstate crossing. We will further see what is intersymbol crossing and interstate crossing. Here we can see that the electron at the ground state is excited, and from this it is going to another excited state, lower excited states. This is called intercrossing, because it is happening in the same atom. Intersymbol crossing is nothing but when the excited electron is going to the excited state of another atom in the material, then we can say it is as interstate crossing. Due to interstate crossing, we have a process called phosphofluorescence. Here, interstate crossing happens between energy levels of the same atom, and because of this time difference, the phosphofluorescence process is it is slower than fluorescence phenomenon. Fluorescence is generally very fast, which is nanosecond delay time, and some fluorophores have longer delay times. This can be used to improve signal to noise ratio. Phosphorescence lights are usually in our day-to-day life. We can see the phosphorescence lights where even after we switch off the light, we can see that it is still emitting some amount of light. This is due to the interstate crossing happening in the device. This is the spectroscopy of fluorescence. Here we can see the energy emitted by the sample tells us about the frequency of emission. Historically, fluorophores are rhodamine and cyanide. This phenomenon is used to identify cancer cancerous cells from the wavelength emitting by them. Several companies sell fluorophores like Agen, Thermo Fisher, and so on. Here we can see the sample, the light emitted by the sample is concentrated on the beam splitter with the help of a lens, and which is again used and which is excited by the source. The combined result we can the emitted wavelength the detector sees and tells us which material is the sample. Now, spontaneous emission. Spontaneous emission is nothing but if an electron in an atom in initially upper energy level, it may decay spontaneously to lower energy level and release its energy in the form of a photon. The photon energy is added to the E of the electromagnetic mode. This process is called spontaneous emission because of the transition is independent of the number of photons that are already made in the mode. Stimulated emission. If an electron in an atom is in upper energy level and the radiation mode contains a photon, electron may be induced to emit another photon into the same mode, clone photon with precisely same characteristics of the original. This is called stimulated emission. This is inverse of this photon amplification process is the phenomenon that underlines the operation of laser amplifiers and sources. Here, a laser is a light amplification by stimulated emission of radiation device. Laser is a device that emits light through process of optical amplification based on the stimulated emission of electromagnetic radiation. Here we can see stimulated emission allows a photon in a given mode to induce an atom whose electron is in upper energy level to undergo a transition to a lower energy level, and in the process to emit a clone photon of the same mode as of initial photon. A clone photon has same frequency and wavelength, direction and polarization as that of initial photon. These two photons in turn serve to stimulate the emission of two additional photons and so on while preserving the properties. This result is called coherent light amplification. Here, what happens is, let's say a photon and a wave is starting from at this point, and the wave, these two are, this is a light laser source. How laser source is, how a light is emitting from the source. Let's say there is a wave starting at this point, and these two are highly reflective mirrors. One is a highly reflective mirror and other is a partially reflective mirror. What happens is when this wave travels through this mirror and gets reflected back and travels to this mirror and so on. It keeps on reflecting back and traveling. Since the energy is stored in this, some of the reflected wave, some of the energy, because of this is partially reflected, some of the energy comes out of as light source. This since the wave is traveling to and fro, only a particular wavelength sustain in this cavity, and only few wavelengths come out of the cavity, and other wavelengths get destructively interfered and cancelled each other. That is the reason why in a laser source, we can, depending upon the distance and reflectivity properties and the gain of the medium which is in the cavity, we can say that only few wavelengths can be extracted from a laser source. Because the stimulated emission occurs only when the photon energy is equal to the atomic transition energy difference, the process is restricted to a band of frequencies determined by the line width of the laser. Here, as I said before, this coherent optical amplifier is a device that increases the amplitude of an optical field while maintaining its phase. related to the input when the phase remains unchanged, or it is shifted by the underlying principle of achieving the coherent amplification of light is known as laser. Incoherent optical amplifiers are nothing but increase the intensity of optical wave without preserving its phase. The arriving photon stimulate a photon, and in a coherent optical amplifier, arriving photon stimulate a photon, produce a clone photon, has same properties of the initial photons. They go on stimulating. In a coherent optical amplifier is the principle behind lasers. Incoherent optical amplifier amplifying is the principle behind LEDs. Lasers are fabricated, or laser sources are made from direct bandgap semiconductors. Direct bandgap semiconductors are nothing but where the moment there are two types of semiconductors, direct bandgap and indirect bandgap. In direct bandgap, the momentum changes. Here we can see that in direct bandgap, to move an electron from one lower energy state to higher energy state, the momentum is preserved. Whereas in indirect bandgap, there is a change in the momentum to move an electron from lower energy state to higher energy state. That is the reason why we cannot fabricate lasers using indirect bandgap semiconductors. Laser amplification. An essential ingredient for achieving laser amplification is the presence of the greater number of electrons in an atom. In the upper energy level, such that stimulated emission happens. If we have larger electrons in the upper energy levels, then we can large amount of photons can be released. To have larger amount of greater number of electrons in the upper energy level, we do something called population inversion. What is population inversion? Laser amplifiers require an external source of power to provide the energy required to augment the input signal. We pump the power via mechanisms that excites the electrons in the atom, which causing them to move from lower energy level to higher energy levels, thereby increasing the density of number of electrons in higher energy levels. To achieve the amplification, the pump must provide a population inversion. The pumping can be achieved optically, electrically, or chemically also. Here we can see that optically pump can be achieved with a flash lamp or a laser with smaller wavelengths, with a different wavelength. For a 1550 nanometer laser, we have a pump of 980 nanometer. Electrically, we can use a gas discharge and an electron beam or ion beam. Chemically, we can use with a flame via chemical reaction that leaves the product in excited state. Ruby laser is used chemically. Here, laser amplification, the average density of the absorbed photons is let's say this is N1WI, and the photons generated by the stimulated emission is N2WI. The net would be the difference between the density between the stimulated and absorbed. If the net is positive, we can say that the population inversion exists. If the net is negative, that means the more number of electrons are present in the lower energy state than higher energy state. We can say the medium acts as an attenuator. If an electrical pump providing a population inversion, that is when N greater than the net density is greater than 0, causes a photon flux density which keep on increasing as the wave travels in the medium, as the clone photons keep on increasing. This is because the emitted photons stimulate further emissions, and the growth at any position Z is proportional to the population at the position. We can see at the end of the medium, we have a higher intensity and there is a spread between, it's not an impulse, theoretically it should be an impulse, but there is a spread because of the, since energy levels, higher energy levels are not just a single energy levels, they are a band of energy levels, and due to this, since they are closely packed, we can see different frequencies coming into picture. Rate equations. The equations thus describe the rate of change in population densities as a result of pumping, as well as radiative and non-radiative transitions overall lifetimes tau1 and tau2. The lifetime of level 2 has two contributions, one associated from the decay from 2 to 1 and the other associated from 2 to 0, that is decay from 2 to any other lower levels that are present. When several modes of decay are possible, overall transition rate is the sum of the component transition rates. Since the rates are inversely proportional to the decay times, the reciprocal of the decay times must be added. Aside from the spontaneous radiative emission component, that is tau21, a non-radiative emission component is also present, which may be occurred due to the collision of an atom with the container or with the walls or with the reflector mirrors and so on, which causes a depopulation. That means it doesn't result in a photon. It doesn't result in a photon generation, but it results in something called a phonon generation. It's just a release of energy, which is not having the same properties of our clone photons. If a unpumped system like illustrated in the figure 1 is allowed to reach steady state, the population densities N1 and N2 will vanish by virtue of all the electrons having ultimately decayed to the lower energy levels. Steady state populations of level 1 and 2 can be maintained, however, if the energy levels above level 2 are continuously excited by pumping and ultimately populating level 2, as shown in more realistic level energy diagram in figure 2. By means of pumping, the population density of level 2 is increased at a rate R2, while that of level 1 is decreased at a rate R1. We can say, for the population inversion to sustain, we need more number of electrons in our level 2. So we need to pump. Pumping should be more such that level 2 has more electrons than lower levels. In this, this is a 4-level pumping. In this arrangement shown in the figure, level 1 lies above the ground state, which is designated as level 0. In thermal equilibrium, level 1 is usually virtually unpopulated. Third level is involved and which is used for pumping. And 3 to 2 decay is so rapid so that there is no buildup of population in level 3, and the decay from the electrons are long lived at level 2 because they have to wait for the arrival of the photons, which accumulates population, and whereas level 1 is short lived so that it sheds population, and so that the electrons shed from level 1 goes to ground state, and they can again be used for they can again be used for population inversion. The upper laser level, which is long lived, therefore accumulates population as electrons are pumped from level 1 to level 3 by absorbing light at a frequency E3 by H at a rate R. Fast decay effectively pumps level 2 at the rate R2. The thermally excited population of level 2 is assumed to be negligible. This is a 3-level pumping. Here we can see that a 3-level pumping, in contrast to the 4-level pumping, there is no ground state or other lower level states, everything was considered as one. Here we do pump from ground state to third level. There a rapid decay has to be seen so that level 2 accumulates population, and the electrons in the ground state should also be short-lived, so that again they can be used for population inversion. Level 3 is involved, as it says. Third level is involved, and the 3 to 2 decay is so rapid that there is no build-up population in level 3. Optical fiber lasers. Optical fiber amplifiers are usually used for amplifying the media. It was the sources are they can be used as sources also. They are doped with rare earth elements like erbium, ytterbium, and so on. However, among all, the erbium are exception, as they operate efficiently in usually telecommunication bands, that is 1550 nanometer. Here, the signal is amplified via stimulated emission provided by downward electron transitions to the pumped ions. As shown in the figure, the pump light may be injected in the same direction as the signal, or in the opposite direction, or in both directions. Ruby laser is the first type of laser to be constructed. It produces red light. A ruby laser is a 3-level pumping device in which chromium ions replaces a small percentage of aluminum ions. Here, level 1 is the ground state, and level 2 comprises of closely spaced discrete levels. Level 3 comprises of 2 broadbands centered about 1550 nanometer, which is of green wavelength, and 400 nanometer, which is of violet. These absorption bands are responsible for the reddish color of the material as the light passes through the ruby rod, which was optically pumped from level 2 to level 3 by surrounding it with a helical flash lamp, or by enclosing it together with a linear flash lamp within a reflecting chill cylinder of electrical cross-section. The flash lamp emits white light, and the ruby rod absorbs violet and green color and emits red color. A fraction of this white light is absorbed by level 3 and resulting in the excitation of chromium ions to the level 3. Excited chromium ions rapidly decay from level 2 to 3 in the order of a picoseconds, and they stay there at level 2 for a sustainable time, since spontaneous lifetime from 2 to 1 is about 3 microseconds, which is the case of a 3-level pumping device. Here, non-radiative decay is negligible, and the transition has a homogeneous broadened line width of 330 gigahertz, principally due to elastic collisions, which are caused by the elastic scattering, which we will discuss in the nonlinear optics phenomenon. The next important laser is a medium of laser. Here, we use the pump of 1808 nanometer, and using a crystal-like structure, we emit 1532 nanometer, and also we get another 2 wavelengths are possible as an output. Optical pumping by a semiconductor laser diode at 808 nanometer populates the 1.53 electron volt. This laser also supports 1340 nanometer and 1940 nanometer respectively. The transition from 3 to 1 is responsible for the laser action of 1064 nanometer. Here we can see that the frequency doubling happens. When frequency doubling happens, this transition provides familiar green line transmission at green wavelength emission at 532 nanometer. Laser is an optical oscillator. It comprises a resonating optical amplifier whose output is fed back to the input with the matching phase. Feedback is endangered by placing the active medium in an optical resonator which reflects light back and forth, as I said earlier. Because of this, only particular frequencies comes out, and we can see that the separation between the frequencies which are transmitted from the output has depending on the distance between the mirrors. And once let's say the medium has a loss and we need wavelength with certain amount of gain. Only the frequencies which are getting transmitted from the source having a higher are in the region of the gain region are taken into consideration, or those are the frequencies only which are seen by the user. The wave propagating between the cavity mirrors due to the constraint of separation between the reflecting mirrors, only few frequencies get constructively interfered. These frequencies having gain higher than the absorption loss of the medium in the cavity radiates out of the laser. This allows only few frequencies as the output of the laser, and as I said earlier, these frequency modes depend on the free spectral range. A laser is a monochromatic, that means have only certain frequencies or certain wavelengths. As we can see, only few wavelengths are being transmitted, and directive, that means it is directional, and coherent light source. As laser source is mainly due to stimulated emission, they have the same phase. All the photons are same in phase, constant phase, that is resulting in a coherent light source device. You can construct it in two ways: surface emitting and edge emitting. Surface emitting LED is designed for optical fiber communication at a wavelength of 1.3 micrometer. Edge emitting is a super illuminescent diode which generate light with a substantial optical power and bandwidth intermediate to that of LED and laser diode. Surface emitting LEDs emit from the face of the device, and that is parallel to the plane of active region, that is the depletion region. The edge emitting LEDs emits from the edge of the active region. A photodetector is a device that measures the photon flux or optical power by converting the energy of the absorbed photons into a measurable form, usually in the form of current. This operation of converting the absorbed photons into current is called photoelectric effect. Absorption of the photons of a material causes electrons to transit from to lower energy levels to higher energy levels, resulting in mobile charge carriers, holes at the ground state, electrons at the higher states. Under the effect of electric field, these carriers move and produce a measurable electric current. The photoelectric effect takes of two forms, external and internal. As illustrated here, the image of a metal for external photo effect is illustrated. The external photo effect involves photoelectric emission, in which the photo-generated electrons escape from the material as free electron. If the energy of the photon illuminating a material is sufficiently large than the barrier or the potential barrier of the surface, then it can liberate the electron into vacuum, calling it as a free electron. The incident photon energy releases a free electron from within the partially filled conduction band. Here, the photoelectric work function is the energy difference between the vacuum level and the Fermi level of the matter. This is called Einstein's photoelectric emission. I'm sorry. the internal photoelectric effect. Photoelectric emission from an intrinsic semiconductor is portrayed schematically in figure. Photoelectrons will usually released from valence band where electrons are plentiful. The formula is given here. Internal photoelectric effect involves photoconductivity, in which the excited carriers remain within the material and serve to increase its conductivity. E.g. is the energy band gap, as zeta is the electron affinity of the material. Electronegativity is defined as the ability of an atom to attract the electron. Negative electron affinity, that is, which is electronegativity, are used for photoelectric internal photo effect. That means when theta, the electron affinity, is negative, then we can have an internal photo effect. Phototubes or vacuum. Photodetectors based on photoelectric emission can take form of vacuum tubes called vacuum photodiodes or phototubes. Electrons emitted from the surface of the photoemission material called the photocathode travel to an anode which is maintained at a higher potential. The photocathode can be opaque and operate in a reflection mode or a semi-reflection or a semi-transmission mode. As a result, the electron transmitted from a cathode to anode is proportional to the photon flux that is incidented on the cathode. This is known as photocurrent, and this is we can see the working principle of this in this circuit. There is a second mechanism where the photoemitted electrons may also create a cascade of electrons via the process of secondary emission. When the photoelectrons impact others specially placed semiconductors called diodes, what happens is when the electrons from the cathode fall upon the diodes and they excite other two electrons, and the excited electrons, like one electron gives rise to a clone electron. The clone electron and the excited electron moves to the next diode, giving rise to another two set of each electrons, and so on. This results in an amplification of generated photocurrent by a factor as high as 10 to the power 8. This device is called photomultiplier tube. Photomultiplier tube can be used to detect, count individual photons while offering a large dynamic range. However, for this to happen, we need a high voltage supply, and the circuit is generally bulky. Photoconductivity. Photoconductivity is a phenomenon, optical electrical phenomenon, in which material becomes more electrically conductive due to absorption of electromagnetic radiation. Photons absorbed in the depletion layer generated electrons and holes which are subjected to the local electric field within the layer. The two carriers drift in opposite directions. Detectors based on photoconductivity rely on the light induced increase in the electrical conductivity of the material. The semiconductor, the phenomenon, the processes involved in the photoconductivity are generation, transport, and gain. Absorbed photons generate free carriers, and applied electric field causes these carriers to move, resulting in a circuit current. And gain, in the sense, as we discussed earlier in photomultiplier tubes, where a single electron gives rise to multiple electrons, the gain can be seen in a special photodiode called avalanche photodiode, which we will see in the later slides. This is due to, in avalanche photodiodes, large electric fields impart sufficient energy to the carriers so that they in turn free additional carriers by impact ionization. Photoconductors. When photons are absorbed by a semiconductor, mobile charge carriers are generated. The electrically conductive of the material increases in proportion to the photon flux. An electric field is applied to the material by external voltage source causes the electron and holes to be transported. If the photon energy is greater than the band gap of the semiconductor, photons are absorbed by virtue of band-to-band transition and electron-hole pair is generated. A photoconductor device may be in the form of a slab or a thin film, and the anode and cathodes are contacts often integrated on the surface of the materials. This is the integrated version of a photoconductor. PN junction diode is a homojunction between P-type and N-type semiconductor. It acts as a diode, which can serve in electronics as an rectifier, logic gate, voltage regulator tuner. In optoelectronics, it serves as a light emitting diode, laser diode, photodetector, solar cell, and so on. A PN junction consists of a P-type and N-type semiconductor. The P-type region has an abundance of holes and a few mobile electrons, and N-type has abundance of electrons and few holes. A photodiode is a PN junction whose reverse current, that is, it is reverse biased. Reverse current increases the photon absorption. When the photons are absorbed, an electron-hole pair is generated, but only where an electric field is present can the structure of a photodiode is PN diode. Whenever a photon is absorbed, an electron-hole pair is generated, but only where an electric field is present can the charge carriers be transmuted in a particular direction. Since PN junction can support an electric field only in the depletion region, it is the region which is desirable to generate photocarriers. Here in photodiodes, by applying a reverse high base, the generated electron and holes are separated and the current is measured. The disadvantage of PN diode is that the depletion is really small and it depends upon the depletion region, width depends upon the doping concentrations. Even if we make the length of the PN diode larger, as we keep on increasing the depletion length, the diffusion and drift times increases. That means the reaction time of the photodiode increases, which is not something desirable at high data rate communications. This can be overcome by using PIN diode, which is a special case of photodiode. Here we can see that electron holes are generated in the depletion region, quickly drift in the opposite directions. And there are three possible locations where electron hole pairs can be generated: in the depletion region and in the once they are generated in the depletion region, they quickly drift to the opposite directions under the influence of strong electric field. Since the electric field points in the N to P direction, the electrons move to the N side and holes to P side. As a result, photocurrent is created is always in the reverse direction, that is from N to P. Electron holes generated away from the depletion region cannot be transmitted because of the absence of the electric field. They wander randomly until they are annihilated by recombination. They do not contribute a signal to the external electric circuit. Electron hole pairs generated outside the depletion region but within the vicinity, that is in region 2, have a chance of entering into the depletion region by random diffusion. An electron coming from P side is quickly transported across the junction, therefore contributes a charge to the external circuit. A hole coming from the N side also have a similar effect. As we can see, increase in the PIN diode, increasing the width of the depletion region or device increases the area available for capturing of light. Rather than increasing the width of PN junction, we place an intrinsic material between the both P and N an intrinsic layer is sandwiched between P and N. The energy band diagram, the charge distribution, the electric field for a reverse biased PN diode is illustrated in the figure. The working of a silicon-based PIN diode is that though we have a larger capturing area, and also the transit time is really small compared to photodiode, because the P and N are heavily doped and the charges are free mobile carriers are present, and they can the capturing area is large, and the I is intrinsic, which is something we don't have any carriers, which causes the depletion to happen really quickly. The advantages of the pin structure is that quantum efficiency, sensitivity, gain of the device can be controlled by the thickness of the intrinsic region, while thin P and N regions can be maintained. Avalanche photodiode operates by converting each detected photon into a cascade of moving carriers. Weak light is able to elicit a current that is sufficiently large so that it can be detected by the electrons following the avalanche photodiode. This device is configured as a strongly reverse biased photodiode in which the junction electric field is large. The charge carriers can therefore acquire sufficient energy to excite new carriers by the process of impact ionization. The semiconductor photodiode detector is in PN junction structure is also based on the internal photoeffect. Photons absorbed in the depletion region can be generated electron and holes which are subjected to the local electric field within that layer. The two carriers drift in opposite directions. This transport process induces electric current in the external circuit. Some photodetectors incorporate internal gain mechanisms so that the photocurrent can be amplified by carrier multiplication within the detector and thus make the signal more easily detachable. Devices in which internal amplification process occur are known as avalanche photodiodes. The figure of merits of a photodiode detector are usually quantum efficiency. Suppose quantum efficiency is nothing but the probability of a single photon incidented on a device will generate a photocarrier. It is the ratio of number of electron voltages generated and collected by the incident photons. And the second figure of merit is K. When the light falls on the semiconductor, the excess carriers are generated. Suppose the electron travels faster than holes when the light falls on the semiconductor, excess carriers are generated, and the gain formula is given as this, where TRN and TRP are the transit times of electrons and holes, and to reach the diodes. The devices like the avalanche photodiodes exhibits internal gain because of the recombination lifetime and transient time generally differ. Suppose the electrons travel faster than holes and the recombination time is very long. As the electron and holes are transported to the opposite sides of the photoconductor, the electron completes its trip sooner than the hole. That is how the gain is varied between depending upon the holes and the electrons. This other figure of merit is responsividity. The responsividity of a photodetector relates the electrical current flowing in the device circuit to the optical power incidented on it. As we can see, responsibility increases with wavelength, but after a cutoff wavelength, due to the bandwidth separation of the material, it just decreases. If photon were to generate a photocarrier pair in this device, a photon flux would produce an electron flux in the circuit corresponding to a short circuit electric current. This electric current by the circuit and the photon power is related through responsivity.